Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome you all, the student of class 11, for our chemistry lecture. As we have started chapter number 7, that is modern periodic table. This is our 12th lecture for the same. In our previous lecture, we have started the topic periodic trends in physical properties of elements in modern periodic table. We have completed periodic trends of in physical properties of elements in modern periodic table. In that we have completed atomic radii and ionic radii. Today we are moving forward towards ionization enthalpy. What is ionization enthalpy? Removal of an electron. Remove means to take out an electron from the neutral atom. Whatever your neutral atom is there, when we remove an electron from that atom, it will result in formation of cations. Fine? Any of an atom, when it removes an electron, it will be converted into cations and positive charge will develop on it. So, the energy required to remove an electron from the isolated gaseous atom in its ground state is called ionization enthalpy. How much amount of energy is required? How much amount of energy is required to remove an electron from the isolated gaseous atom in its ground state is nothing but your ionization enthalpy. It is denoted by symbol delta I, that is ionization. H is the symbol for enthalpy. It is the quantitative measure of tendency of an element to lose electron, and it is expressed in terms of kg, kilojoule per mole. Fine. What is ionization enthalpy, student? It is the energy required to remove an electron from the isolated gaseous atom in its ground state, and it is expressed in kilojoule per mole. Since electrons are lost one at a time only one electron is being taken out, then successively second, third, and so on. So these electrons are lost one at a time. We have first ionization enthalpy, second ionization enthalpy, and so on for a given element. So here, student, you're supposed to know, you're supposed to learn it. What is ionization enthalpy? Ionization enthalpy is the amount of energy required to remove an electron from the isolated gaseous atom in a ground state, and it is expressed in terms of kilojoule per mole. And one electron are lost at a time. So we are having first ionization and B, and then second, and then so on. So here you see student X, it is a neutral gaseous atom. It has liberated one electron. Fine. Here X, G means it is in gaseous state. X means any of the neutral atom, and G, it has been written in bracket, it means it is in gaseous state. Arrow is there. It liberated one electron plus E minus, as electron carries negative charge, E carries negative charge. E is the symbol for electron, minus charge is the charge which an electron is carrying. So this neutral gaseous atom, when it liberate one electron, it get converted into cations. So one electron is liberated, so plus one positive charge. Okay, so this one positive charge in the next step, in the first step we have giving the symbol for ionization enthalpy delta I H1. H1 means first ionization enthalpy. In the second step, this cations X plus in gaseous state, will liberate its second electron. So plus 1 will be converted into plus 2. Fine. In the first step, neutral gaseous atom liberated 1 electron get converted into plus cations. While in the second step, plus your elements, it liberated its second electron, that plus charge has been converted into 2 plus. Okay, and this is your second step for ionization enthalpy. It has been represented by H delta I H2. So your ionization enthalpy is always positive. Yes, it will be always positive. When it is liberating out, it is knocking out its electron. Since the energy always need to be supplied to knock out electron from atom. Okay. Why ionization enthalpy is always for positive? Because the energy always need to be supplied to an atom to knock out an electron from it. Okay. So here the second ionization enthalpy is larger than the first ionization enthalpy, as it involved removal of electron from the positively charged species. Okay. Here in the neutral gaseous atom, no electron has been removed out. Okay, so the last electron can be liberated out easily, but as it has liberated out 1 electron, it has been converted into positive charge. So as it has been converted into positive charge, we require more amount of energy to be liberated out from that positively charged species. So always remember, the second ionization enthalpy is larger than the first ionization enthalpy. Similarly, to remove out the third last electron, X2, when X2 is there, it will get 1 electron, it will get converted into X3 plus. So we require more amount of energy. The third ionization enthalpy will be greater than the second, and the second in turns will be greater than the first. What is the reason? Because it involves and removal of electron from the positively charged species. Here you see it, student, table number 7.3. First ionization enthalpy values of element in group 1. Group 1 element lithium, sodium, potassium and so on. Atomic number has been given. Its outer electronic configuration has been given. What do you observe from the table? It is seen from the table that on moving down the group, the first ionization enthalpy decreases. This is because, you see, with the values down the group, it is 520, then 496, then 419, then 403, then 374. So down the group, the first ionization enthalpy decreases. This is because electron is to be removed from the larger valence shell. Why? Because the number of shell is been increasing. For lithium, it is 2 number of cells, sodium 3, potassium 4, and so on. So here the number of shell is been increasing. So electron is to be removed from the larger valence shell. And screening due to core electron goes on increasing. Screening effect will increases. Why? Because the number of shell is increasing. And effective nuclear charge decreases down the group. We have studied what is screening effect, what is effective nuclear charges. Okay, so here screening effect is been increasing and effective nuclear charge decreases down the group. So the removal of the outer electron therefore become easier and more easily. If the electron can be easily removed, then we require lesser amount of energy. Fine, we are doing some work. Okay, if that work is hard, we require more amount of energy. If that work is easy, we can easily do that work. Okay, so here as the number of shell is increasing, valence shell is increasing, screening effect is also being increases and nuclear charge is being decreases. So the removal of the outer electron become easier, more and more easy. Okay, so in this case we have seen down the group, the first ionization enthalpy is being decreases. Now you see the table 7.4. Elements of periods 2: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So here student, what do you observe? The number of shell is being same. Okay, and the first ionization enthalpy value for first element, that is for lithium, is 520, beryllium 899, boron 801, carbon 1086, and so on. And overall increase of the first ionization enthalpy across the period. You see the value 520, 899, and so on. It has been moved to 2018. What do you observe? That the first ionization enthalpy value has been increases. Why? Because the valence shell is same and screening effect is the same. As the number of shell is same in all of these elements, the screening effect will be same. But as the number of proton is increasing, the effective nuclear charge increases across the period. Okay, as the effective nuclear charge has been increasing, as a result the outer electron is held more tightly. The electron will be held more tightly. So the first ionization enthalpy therefore increases across the period. Down the group, the first ionization enthalpy is decreasing, while across the period the first ionization enthalpy is increasing. Okay, the alkali metal display the lowest first ionization enthalpy. The inert gas shows the highest first ionization enthalpy across the period. Where alkali, lithium is an alkali metal. Okay, neon is your zero group element. That is, neon is having the highest first ionization enthalpy. You see the value. Its value is 2080. While lithium, that is having the value 520. It is having the lowest first ionization enthalpy. In short, across the period, the ionization enthalpy is increasing. In the table, you see some irregularity between beryllium and boron. As the first ionization enthalpy is increasing across the period, you see there is a value for beryllium is 89 and for boron it is 801. It has been decreasing. So, you see some irregularities which has been noticed for the first ionization enthalpy as we move across a period. The first ionization enthalpy of boron is smaller than that of beryllium. Why? Because beryllium loses the electron from 2s orbital. Beryllium loses the electron from 2s orbital while boron loses the electron from 2p orbital. Fine. You see, beryllium, it is losing the electron from 2s, while boron, it is losing the electron from 2p. See, beryllium outer electronic configuration 2s2, for boron 2s2 2p1. So beryllium is losing its electron from 2s and boron is losing its electron from 2p. So here, this is the reason beryllium loses the electron from 2s orbital, where boron loses the electron from 2p, which has less penetration. We have been studied this in chapter number 4, that is structure of atom, shape of orbital. Okay, so then the 2s orbital, therefore it is easier to remove a 2p electron than a 2s electron. We can easily remove the electron from 2p orbital as compared to 2s electron. Similarly, first ionization enthalpy of oxygen is smaller than that of nitrogen. Why? Because oxygen loses the electron from a doubly occupied 2p orbital. Oxygen form double bond. Okay, due to electron-electron repulsion, an electron-electron, there will be repulsion. It is easier to lose this electron to an electron from the singly occupied 2p orbital in nitrogen atom. So as here in oxygen, doubly occupied 2p orbital is there, while in nitrogen singly 2p orbital is there. So in oxygen, electron repulsion will take place, due to which it can easily lose its electron. We have studied this in chapter number 4, Hund's rules of maximum multiplicity. We stated this rule. Okay, so oxygen is having smaller first ionization enthalpy than that of nitrogen. This is a numerical for you, student. The first ionization enthalpy value of silicon, phosphorus and chlorine are 780, 1060 and 1255 kilojoule per mole respectively. Predict whether the first ionization enthalpy of sulfur will be closer to 1000 or 1200 kg per mole. Okay. This is the question. The ionization enthalpy of silicon is being given, phosphorus is being given and chlorine. You have to predict out the first ionization enthalpy of sulfur, which will be closer to 1000 or 1200 kilo per mole. As we are moving across the period 3 from left to right, the elements silicon comes, then phosphorus, then sulfur, then chlorine come in a sequence. Okay, silicon, phosphorus, sulfur and chlorine. Their outer electronic configuration has been given. For silicon it is 3s2 3p2, for phosphorus 3s2 3p3, for sulfur 3s2 3p4 and for chlorine is 3s2 3p5. As we are moving across the period 3 from left to right, the elements silicon, phosphorus, sulfur and chlorine comes in a sequence. The outer electronic configuration for silicon is 3s2 3p2, phosphorus 3s2 3p3, sulfur 3s2 3p4 and chlorine 3s2 3p5. Okay, phosphorus loses an electron from a singly occupied 3p orbital. Okay, whereas sulfur loses an electron from a doubly occupied 3p orbital. Yeah, phosphorus loses its electron from singly occupied 3p orbital, while sulfur loses from doubly occupied 3p orbital. Therefore, the first ionization value of sulfur has to be lower than that of phosphorus, as we have studied earlier this criteria. So here also similarly, the first ionization value of S has to be lower than that of P. Hence, first ionization enthalpy of sulfur will be less than 1060 kg. Okay, it should be less than 1060. Why? Because we have studied the criteria. Sulfur loses an electron from a doubly occupied. It can easily remove an electron. So it should be lower than that of phosphorus. So as the value for phosphorus is 1060, its value should be lower than that of phosphorus. Its value should be lower than 1060. So which value it should be? It should be your 1000, not 1200. So its value should be 1000 or close to be 1000. Okay, and therefore its value should be close to 1000 kilojoule per mole and not 1200 kilojoule per mole. In this way, we can find out the first ionization enthalpy of any of the element. Hope student you have understood. You are supposed to know what is ionization enthalpy, how much amount of energy is being required to remove an electron from an isolated gaseous atom. It is expressed in terms of kilojoule per mole. Okay, in short, we are summarizing the lecture. What is ionization enthalpy? The amount of energy required to remove an electron from an isolated gaseous atom. Ionization enthalpy is expressed in terms of kilojoule per mole. First ionization enthalpy is greater than the third ionization enthalpy is greater than the second one. Second in turns is greater than the first one. Okay. Across the period, ionization enthalpy is been increasing. Down the group, first ionization enthalpy is been decreases. Okay, and we have solved a numerical for the same. Hope you all have understood. Study well. Take care. Thank you, student. Allah Hafiz.